radial field. According to the above formula, the strength of the current is not proportional to the deflection phi, hence the current cannot be read directly. To remove this difficulty, it is necessary that in every position of the coil, the plane of the coil be parallel to the magnetic field so that the deflecting torque always be NIAB. It is for this purpose that the coil is suspended between cylindrically cut pole pieces and a soft iron core is placed within the coil without touching it anywhere. Then the magnetic lines of forces are no longer parallel, but their distribution becomes as shown in figure. Due to the large permeability of soft iron, more lines of force pass through the core and thus makes the magnetic field strong. Such a magnetic field is called radial field. In this field, in every position, the plane of the coil remains parallel to the lines of force. That is, in every position, theta equal to 90 degree. Hence, the deflecting torque on the coil suspended in radial magnetic field is always NIAB. Then, in equilibrium position, we have NIAB equal to C phi or I equal to C upon NAB phi or I equal to K phi, where K equal to C upon NAB is a constant which is called the reduction factor of the galvanometer. Thus, I proportional phi, that is the current flowing in the coil, is directly proportional to the deflection of the coil. Now let's see sensitivity. A galvanometer is said to be sensitive if a small current passed through it produces a sufficiently large deflection. The sensitivity is of two types: current sensitivity and voltage sensitivity. The current sensitivity of a galvanometer is defined as the deflection produced in the galvanometer when a unit current flows through it. If a current I produces a deflection phi in the galvanometer, then the current sensitivity is phi upon I. By equation 1, we have phi upon I equal to NAB upon C. The reverse of current sensitivity is known as figure of merit of the galvanometer. The voltage sensitivity of a galvanometer is defined as the deflection produced in the galvanometer when a unit voltage is applied across its coil. If a voltage V produces a deflection phi in the galvanometer, then the voltage sensitivity is phi upon V. If R be the resistance of the coil of the galvanometer and I the current through it, then V equal to IR. Thus, the voltage sensitivity is phi upon V equal to phi upon IR. Putting the value of phi upon I from equation 2, we have phi upon V equal to NAB upon CR. Equation 2 and 3 show that the sensitivity of a galvanometer can be increased by increasing the values of N, A and B and decreasing the value of C. However, N and A cannot be increased beyond a limit, otherwise the resistance and also the mass of the galvanometer coil would increase undesirably. Therefore, B is made as large as possible and C as small as possible. The magnetic field B is increased by taking a very strong horseshoe magnet and placing a soft iron core within the coil. The core concentrates the lines of force. The torsional constant C is made small by using a long and fine suspension strip and a thin spiral spring of phosphor, bronze or quartz. The quartz fibers are silvered to make them conducting. A suspended coil galvanometer can measure currents of the order of 10 power minus 9 ampere. In the suspended coil galvanometer, the suspension strip is very delicate and may be broken by a small jerk. Therefore, the galvanometer cannot be taken from one place to another. This difficulty has been removed In the western galvanometer,